2-3 today. We're gonna be moving through it pretty quickly. We didn't finish all the review questions, but, for example, the table on the top of page 79, in the review Q2, number 8, you can, if you haven't finished that, look up the answers. I don't think any of those questions are particularly challenging. The question on the top of page 80, number 13, complete the following table by putting check marks in. That's maybe not a bad one to have a look at. It's consistent with that summary table that Gary gives us at the end. And again, as he mentions, there's no hard and fast distinction between where a solution stops, where a colloid starts, where a colloid stops, and where a heterogeneous mixture starts. It's really just a matter of good view. So see it kind of as a spectrum rather than, 3 separate categories, okay? 2-3 is kind of on the heels of what we were doing in the matter map with respect to mixtures. Remember, mixtures are components that are physically combined. The idea is if they're physically combined, you should be able to take advantage of physical property differences to physically separate them, meaning there's no chemical events required to separate components of a mixture. If you look at the warm-up, which I don't often do, but if you look at the warm-up, a student scoops up a pail full of water and mud from the bottom of a pond. The mixture in the pail is a suspension of mud particles, algal cells, and a solution of salts. Outline a method for separating these 3 components. And I think Gary's point behind that is, can you connect what we did in section 2.2 with what you might already know? So what would you do, step 1? What would be the first thing you would do to separate the components? Outline a method for separating these 3 components. What are the components? Mud particles, algal cells, and a solution of salts. So the idea is, at the end of your procedure, you should have those 3 things separated from each other. Don't access what you might have tried to memorize, just common sense. What might be a first step? What are the components? Heterogeneous mixture, correct? Mud particles. So what might you do first? Filter. Yeah, filter. I asked you to read several pages in 2.4. Okay, mechanical separation, non-mechanical. One of the ones he focuses on in mechanical is exactly that. So that's one type of separation technique. What is filtration taking advantage of? What differences in the components does it rely on to work? Any of you ever made coffee in the morning? That's filtration. Why do the coffee grounds stay in the filter?
They're solid.
Sorry?
They're solid.
Yeah?
Because they're too big.
They're too big? Yeah. Filtration takes advantage of a very obvious property difference, size. The liquid is composed of molecules, particles, small enough to fit through the pores in the filter paper. But the solid particles aren't. And if you let it sit long enough, the solid particles would sink to the bottom. It would form a sediment at the bottom. Now, there's 2 ways to separate the liquid from that sediment, if you had the time to let it sit to the bottom. What's another one that Gary mentions besides filtration? Filtration is faster because you don't have to wait for the sediment to settle to the bottom. But let's say you didn't have, and I'll demonstrate a filtration apparatus in a second. Let's say you didn't have filter paper and a funnel and a ring. What might you do that would be close to as efficient, but not quite?
Wait for the different components to settle.
Talk louder, what?
Wait for the different components to settle
Okay, we're there already. Okay, the sediments on the bottom, then what would you do? What do you call what you do next?
I don't remember.
It's in this section of mechanical separation.
Decanting.
Decant, very good, decant. What you do when you decant is you carefully pour the liquid off the solid sediment sitting in the bottom. You don't wanna do it quickly, because if you do, you're gonna generate turbulence and you're gonna mix it up again. And I'll demonstrate decanting, but maybe a good gut check on those pair of questions, you guys, is when I say or ask, because I can't force you, to read the material, don't equate that to no homework. Remember, I don't give homework primarily for marks. And it makes our discussion a lot more valuable to you if you've already looked at the material before I talk about it. And ideally, there should be some practical application to what you're reading. Here's one right now. Here's a simple problem. You could filter it, you could decant it. Now, that's not all you do, because all that would mean then is now you have the solid, the mud, particles, and you have the liquid portion. What's still in the liquid portion? Read the question carefully. A suspension of mud particles and algal cells and a solution of salts. So now you have a liquid that has two different things in it, according to this. We've got a suspension of algal cells, we've got a solution of salt. So what would plan B be? Then what? Boiling it? I don't know if boiling it is what he's after there. Before we can get into talking about that, I think you might be talking about simple distillation. But before that, how do you get the algal cells away from the solution? Those are the two components remaining in the liquid stuff that goes through the filter grid. You got the mud particles, fine. Let's go back to the table on page 76. You got a solution of salts, and you got a suspension with algal cells. What column has a yes and no for those in it? Sediments, if left undisturbed, well, we've already handled that. We've already separated the solid stuff. But now you've got algal cells and a solution in that liquid. What's the next one where there's a separation technique you could employ that has a no in front of one of them and a yes in front of the other? Centrifuge, yeah. Now you're separating by density. So if you now put the solution of salts and the algal cells in the centrifuge and spin it, the denser algal cells will separate in the bottom. And then probably decanting would be the next choice. Okay? The algal cells are big enough or small enough to fit through the pores in filter paper, but they're denser than the solution, so they will separate by a centrifuge. And again, I'll demonstrate a centrifuge for you, time permitting. We have another critically academic important event happening today that forces us to shorten blocks, known as activity. I will leave it to your intelligence to conclude following the advisory if it was actually worth it, but in any event. Now, this is not something he intends you to do, but now you have a solution of salts. What do you know about every salt at room temperature? What's its state at room temperature? Every salt. Solvent. Because it's an ionic compound, you've got all those inter-ionic forces in 3 dimensions. So let's say you got a solution of salt. Now the separation technique you would employ is not a mechanical one. So is there a non-mechanical separation technique you read about that might work to separate the salt solute from the aqueous solvent? Because obviously a pond is an aqueous solution, right?
Distillation.
Distillation. Did we have like 3 people that read that stuff? What does distillation take advantage of? What property difference does it take an advantage of? Look at the heating curve we drew on the board. Why does the temperature go up when the solution is boiling? What's boiling? What's going away?
Water.
The water, the solvent, yes? Didn't we conclude that at the end of the boiling process, you're gonna have the solid salt remaining in the water? Yeah. So why is the salt still there and the water gone?
So that's an extreme
Difference in what?
melting points.
Are we melting it when we,
Boiling.
instead of melting, we're boiling point? Yeah, boiling point. Now, if you wanna recover the solvent, you're just not gonna let the water vapor go away. You're gonna collect it, cool it, and recondense it. That's a distillation effect. So what property differences did we take advantage of that in that warm-up series? Well, first, size. Filtration is a mechanical separation technique that separates components of a mixture by size. Second one, centrifuge, that's density. Third one, distillation, that takes advantage of boiling point difference. Now, simple distillation doesn't work for mixtures or doesn't work nearly as well for mixtures where you've got a liquid solute and a liquid solvent, often because the boiling points are too close together. And sometimes you got a whole bunch of liquids mixed together, and then you need something called fractional distillation. But we're probably not gonna focus on fractional distillation too much. But the reason I wanted to at least start on the warm-up is because the procedure associated with that is kind of problem solving. I want these things separated, how do I do it? And why does what I do work? Okay? Most naturally occurring objects and materials are mixtures. And I believe I have now accessed the internet, but I'm too lazy to do attendance. So I'm just gonna press boldly on. Our atmosphere, our natural water systems, the ores and petroleum products such as crude oil, natural gas that we extract from the ground are mixtures. And oftentimes the petroleum that we extract from the ground is a mixture of a whole bunch of organic compounds and hydrocarbons, each of which have different boiling points. And in a refinery, you'll often see these tall columns. Those are fractional distillation columns. And we separate the components of those liquids one at a time based on which has the lower and which has a higher boiling point. But we'll get to that soon. Just as a compound can be, just cross that word out because there's no such thing. Just as a compound can be decomposed, a mixture can be unmixed. It's just that a compound can only be decomposed using chemical means, but a mixture can be separated into its components by physical changes, physical properties that differ. Since the ingredients of a mixture are not chemically combined, they retain their individual identities. The trick to separating the substances is to pick a property that clearly differentiates the substances. And sometimes the separation technique that you employ might actually take advantage of more than one property difference. And that's That's the last separation technique we're gonna talk about, called chromatography. And therein lies the handout that I have on my desk. We may get there today, we may not, because we have short and long. Now, this may not seem like I don't know, an important mixture, but the process is still accurate. Consider a mixture of marbles and beads. Because the marbles and beads don't form any aggregates, they can easily be separated by pouring the mixture into a colander, a bowl full of holes. If any of you remember, put a salad spinner, that's a colander, or spaghetti, pour the water through. It would capture the marbles but allow the beads to pass through. But even if you didn't do that, if you have marbles and beads, they're big enough to see, and they look different. So it's perfectly acceptable to separate them manually by hand. That's a separation technique. Obviously, it's mechanical because there's no distillation involved. It's as efficient, depending on how big they are and how many of them there are, as filtration. Okay. Laboratory technicians perform a tremendous number of separations daily in medical, forensic, and analytical chemistry laboratories to allow the substances in the mixtures to be identified. And that's particularly true in forensics, but it's also in medical. If you're trying to find out what, let's say somebody's suffering from some kind of poison, and you have to find out what that poison is. Well, you have to perform a series of tests to see which poison that is, and a lot of times it's separating. You draw some blood, and then you separate the components of the blood until you identify where in that liquid that toxin is. But you've got to start with a sort of a stepwise procedure, kind of like what we did with the pond water, but obviously a little more involved. Anytime an athlete is suspected of doping or chemically enhancing their performance, they do separation techniques, analytical, to find out what that component might be if it's there, okay? Large industrial scale separations are performed around the world in commercial refineries for sugar, oil, metal, etc. to obtain the target substances for their useful properties, their intrinsic values, and more commonly the use of substances to produce useful mixtures of their own design. That's especially true in organic chemistry, which hopefully we'll get to later. Later in your study of chemistry, you'll examine separation technique called selective precipitation. That's a Chem 12 topic we talk about. So you've got a solution, let's say, that has a whole bunch of solutes in it, and you want to separate them one at a time. There's a stepwise procedure you can take advantage of based on what's soluble with what and what's low solubility with the other thing. And it's kind of an interesting application of logic. What are you going to add first? What are you going to add second to ensure that only one of those solutes in the mixture precipitates out at a time, okay? Physical separation techniques include centrifugation, chromatography, recrystallization, decantation, density separation, distillation, electrophoresis, evaporation, extraction, flotation, etc. We're not going to do all of them. Electrophoresis is one of the things used in DNA analysis. He mentions this one, but he doesn't talk about it. And he mentions this, but he doesn't really talk about it. So I'm going to talk about recrystallization, solvent extraction. I'm not too worried about froth flotation. Reverse osmosis, we got to stop somewhere. This one's easy. Let's say you have, we're not going to formally talk about it, but let's say you got a mixture of sand mixed with iron filings. So how would you, well, the iron filings look different than the sand. You could, if you got your whole life, you could probably pick them out one at a time. But what would be the best way to do it? What would be the most efficient way to separate the iron filings from the sand?
Magnetic.
A magnet, passive magnet. Yeah, that's magnetic separation. And we often do that when we're isolating ores. And there's only 3 elements, as far as I know, in the periodic table, they're magnetic. 4, iron, cobalt, nickel, and a rare element called gadolinium, which is down here. Okay. You guys haven't ever taken any magnetism in school, have you? Okay. domains or ferromagnetism, nothing like that. Elementary school, did you ever taught that? Gosh, that's too bad. Anyway, now I don't know that we need to go down all the rabbit holes that Gary goes into here, talking about Isaac Newton. Buoyancy, nah, I don't think we need to worry about that too much. And you're certainly not gonna be expecting to resolve force vectors. Yeah, that's awesome here. So let's talk about filtration first, maybe. Filtration is a mechanical separation technique that takes advantage of different sizes of the particles. I'll show you. I'll show you what it looks like. It's called a ring stand. Lab counterpart of a coffee filter. So, so I don't actually know how this would ever happen, but let's say you accidentally spilled some small tin particles in water and you want it to separate. Would that ever happen? No, probably not. You take a funnel and you take filter paper. It comes in all sizes, all colors, and usually they're circular. And you fold it twice and into that conical arrangement of the filter paper, you pour your liquid. Now I wanted to use sand, but I didn't have any handy. Okay, so I'm using tin. What's coming through the filter paper and collecting in the Erlenmeyer flask is called the filtrate. And Gary labels that for you. What's left on the filter paper is called the residue. Yeah. The only property that that takes advantage of is size. Obviously, the tin is not big enough to fit through the pores, just like the solid particles in coffee aren't, coffee grounds. The water is small enough to fit through the pores, and oftentimes you'll use a glass stirring rod. Do I have any handy here? No. Well, in lieu of that, I'll just use my deformed paper clip of science. Sometimes you can speed it up by moving some of those solid particles around. There's also a type of filtration called vacuum filtration, where the Erlenmeyer flask has a little spout on the side. It's called a filter flask. And you connect it to a vacuum pump, and then the funnel that you add goes in a little jacket that creates a seal. And then when you turn the vacuum pump on, it generates low pressure and it sucks the water out of the filter paper a lot faster, and it also allows for the filtrate to dry, or the residue to dry a lot quicker, okay? It's called a Buckner funnel, but the point is that when you're done, there's the residue, there's the filtrate, okay? And again, the only difference that you're taking advantage of there is size. Now, if instead of filtering, you And maybe I will have to get my stirring rod after all. Let's just say you didn't have one of these handy, okay? Decant the liquid, and because the tin is so heavy, this would be actually a pretty efficient way to do it. You put the stirring rod over the spout in the beaker, and then you carefully pour the liquid like that. And what the stirring rod does is, in the event that some of that tin manages to make its way down to the spout, the water will go past the stirring rod, but the tin won't, okay? So that's decanting. And again, because the tin's so dense, this is actually a pretty efficient way to do it, okay? So both of those take advantage of size and density, okay? Now, we're not gonna go right to chromatography. We got a whole bunch of other stuff to talk about first, okay? One of the things we often do in solution chemistry is we attempt to calculate the solubility of a solute in a solution that's saturated. And to do that, we take a particular volume of the solution and we want to find out the mass of the solute that was in that volume. And this is something we're going to do in terms of calculations when we get into chapter 3. So we perform a separation technique on it that takes advantage, and this isn't a mechanical separation technique, this is non-mechanical. We want to find out how much solute was in the volume of solution. We don't care about the solvent. We take a measured volume of the solution and we put it in what's called an evaporating dish. As the name suggests, you put stuff in it and you evaporate it, okay? And the evaporating dishes come in all shapes and sizes. But what you do is you perform a separation technique called evaporation to dryness. And you put a carefully measured volume of the solution in the evaporating dish, and then you don't boil it vigorously. You heat it carefully because you don't want any of that solution boiling off, like splashing off. And you continue heating it until all you have in the bottom of the evaporating dish is solid residue. Now you weighed the dish before you put the solution in. You record the volume of the solution so you know the volume you started with. Then you evaporate to dryness. You don't care about collecting the solvent because all you care about is the mass of the solute that was in that volume of solution. And then when it's done, you record the mass of the solute sitting at the bottom of the evaporating dish and subtract from that the mass of the dish by itself before you pour the solution. And then you find out the mass of that solid solute that was in the solution. Usually it's an aqueous solution. And then based on the mass of the solid, you can actually calculate what the concentration of that solution was, and we'll talk about that in chapter 3. So that's the separation technique, evaporation to dryness, okay? Takes advantage of different boiling points. Obviously, the liquid solvent is going to vaporize long before the solid solute. That's the separation technique you employ when you don't care about recovering any of the solvent. But let's say you want to recover the solvent. In other words, let's say when you're done, you want the liquid solvent here and the solid solute here. Like, for example, you want to separate salt water from the sea into pure drinking water, and you don't want the salt in there anymore. And that's done all over the world at desalination plants. Well, then you do a separation technique that also takes advantage of different boiling points, except it's not evaporation to dryness, it's distillation. And the difference between distillation and evaporation to dryness is you want to recover the solvent. You don't care about doing that when you evaporate to dryness. You want that solvent to go away. But if you want to recover the solvent, you use distillation. And Gary gives us, and we're not going to worry about fractional distillation. Here's a simple distillation apparatus here. Not there. Excuse me. There. Now I have one in the cupboard there, and I'll show you. I like mine better, but the idea is this. Here's the solution, okay? Let's say it's salt water. You clamp it here, and you've got a clamp there. That's probably a ring with a ceramic pad on it.
This guy got everything in his snap class.
So if you're gonna use that device, or that arrangement, then there's a ceramic pad connected here, or if you want to do that, and then you put your solution that you want to distill on it, and you heat it with a Bunsen flame. And anytime you heat anything that's glassware, you gotta make sure that somewhere on it you see the word Pyrex or Kymax. It's called borosilicate glass, and it's got a low coefficient of expansion, meaning when you heat it, it doesn't expand quickly. And where you cool it, it doesn't contract a lot, which means it's not gonna crack. I mean, it'll still break if you heat it to a sufficient temperature, but it shouldn't if there's a liquid in it and it's over a Bunsen flame. Now, the idea is what boils off is the solvent. And because the boiling point of the solute is so much higher than the boiling point of the solvent, when the solvent boils, that's the only thing in that vapor, the liquid. But you want to recover that vapor. So you force it through a tube known as a condenser. And then the vapor's coming through here. But what's here is cold water. So basically you attach a hose to the lower portion of the condenser, attach it to a tap, turn on the cold water. The water comes up here, goes out there. And as it's passing up here, it's removing heat from the vapor, which is going to condense the vapor. So by the time the vapor gets down here, it drips out as a liquid. And you continue doing it until you have no more solvent here. All the solvent's here, it's been boiled off and recondensed. Now, that's not a bad diagram. I like my distillation apparatus a little better.
Apparatus, that's a funny word.
Who uses like maybe it should be in there. So I need- Perfect. I'm probably not gonna set it up for you because it's gonna take too long.
Oh, he literally did the distillation app. He really wrote it down in the books.
This isn't big enough. What I like most about this is the condenser. It's pretty cool. So the longer that cold water stays in this condenser, and the more efficiently it cools the vapor, the better you're gonna get a liquid condensate over here. So if that water spiraled around the hot gas, it's more efficient at cooling it. So I like that condenser way better, okay?
It's like a,
So the idea here is you connect it to,
it's a dirty ass
I don't wanna break that because that's about $300.
Yo, the Hutchins face.
So you connect the condenser, and again, you gotta clamp all the glassware. If you've got separate glassware, you clamp every bit of it. So you connect the condenser like this. This would be on the stand being heated, like this. Okay. Like that. And you'd use a bigger ring than that. So that's there, being heated. This is here. And you put a stopper here, but sometimes you even put a thermometer. Because sometimes you want a bulb of the thermometer sitting right there, because depending on what the mixture is you're distilling, particularly when it's a liquid mixed with a liquid, you don't want to actually collect the vapor until the temperature reaches the boiling point of the component you want to collect. And at that point, the thermometer is going to sit still at a particular temperature. And that's why you often put the bulb right there, because you're measuring the temperature of that vapor. You force the vapor into here, into the condenser. This goes connected to the cold water, and this just drains into the sink. And that circulates around the gas. So the gas is around, it's in this, but that spiral only contains the cold water, okay? And then you'll eventually get the condensate coming off the bottom, okay? And where do you put the liquid? Well, you put it in Erlenmeyer flask that goes under here, okay? So that's a distillation apparatus. But again, it's obviously a lot more involved than this, but the reason it's more complicated is only because all you care about here is collecting the solid solute. Here you are intent on collecting the liquid, all right, the solid. And we're not going to do a simple distillation, but some high schools actually have distillation apparatuses that, depending on where they are, some actually distill their own drinking water. And it's possible to do that if you want to. It's just that I don't. Especially with that shortened box today,
It's so bad.
I don't really have the time.
I thought this was cool, but then he okay, so, okay.
So we've talked about filtration, decanting. Now, as far as centrifugation is concerned, that's another mechanical separation technique based on density. We've got a little bit of time. So, as luck would have it, our centrifuge.
He just has, he's everything. He's the guy. You need something, you need a nail. He probably has it.
There's no room on my desk, so we'll just put it here.
Nuclear.
Notice that
He's probably got it.
centrifuge has some little suction cups in the bottom. That's usually to help it sit where the centrifuging is happening. And in the event that you forget that you've got to balance what you're centrifuging, those little rubber suction cups will at least hold it reasonably steady before it falls off the end of the table. Okay? So centrifuge is usually what you use prior to decanting. So let me show you what I mean. Not that I wear gloves to centrifuge, I'm just wearing gloves because what I'm pouring together is poisonous.
Yeah.
So
Yeah, just someone beside his office, just a box.
you guys have probably seen this demo
Label candy.
before.
Candy, do not touch.
Here's teachable moment, evidence of a chemical change. Okay, now, to look at that, it looks like you've got a nice homogeneous mixture that's all yellow. But in actual fact, you've got solid particles of lead-2 iodide that are more dense than the solution of, in this case, potassium nitrate that's dissolved in the water. So if I withdraw some of that liquid, and I think these are still on
It's like tar. If he leaves it be, it's gonna settle. It's gonna be like the sediment. Because he says solid
So I couldn't
particles.
really separate the lead-2 iodide from the solution of potassium nitrate. right now because it would take time for it to settle. So let's say I withdraw some of that liquid and put it in my little test tube here. Now again, it looks like a homogeneous mixture, doesn't it?
That's so satisfying.
Well, you take another test tube of equal size. You're gonna put maybe a little more water in here than liquid is in here, because this is more dense than this. That should do it. It might surprise you how little of the yellow solid there is in this test tube, okay? And when we balance it, we want to make sure we put this opposite to the hole that the other test tube was in, and that's why they're all actually opposing each other, okay? And then we turn it on and we wait. And notice that it's not bumping around like a washing machine that has a close on one side when it spins. So let's say you're doing the laundry and you got all the heavy stuff on one side. Then when it spins, it'll go to the other, right? That's what this does too, except it'll jump off the end of the table and fall on the ground, okay? So I'm just gonna let that spin for a while. And then we'll see actually how much of that solid was in the liquid. Now, while it's sitting here, you can kind of see the solid settling to the bottom, but that would take way too long to wait. And if you look on the side of the Erlenmeyer flask, you see how finely divided those particles are. Because literally the lead-2 ions were precipitating with the iodide ions, one ion at a time. And by the way, that reaction that we just performed are among the fastest in chemistry. Precipitation double replacement, where the ions are in close proximity, they can move, they naturally attract each other. So that's about 1/1,000,000th of a second, among the fastest reactions we know. Okay? So the centrifuge is doing the work for me, and it's separating based on density, right? Something that Gary refers to, but he doesn't actually explain an example, is it's again a non-mechanical separation technique. It's called solvent extraction. And as the name suggests, you're trying to extract components of a mixture involving some type of solution process. So let's say that you had, I don't know, sand mixed with table salt, okay? And you wanted to get the sand away from the salt. Now, salt looks a little different than sand, but again, if you tried to individually separate the salt grains from the sand grains, you'd probably be there for the rest of your life. So what might be a really quick first step to use that you might want to try? Can't use a magnet. This is a multi-step event, you guys. What would be step one? Think of what you know about table salt and what you know about sand. And let's say
Sand is denser.
you want to recover the salt in the solid form and the sand in the solid form in their original amounts and purity. What would you do?
You could add water.
Good, louder.
Add water.
Add water. What would water do?
Dissolve the salt.
Would it dissolve the sand? No, that's solvent extraction. Now what difference are you taking advantage of? Obviously not size, not boiling point, not density. But what do you think you're taking advantage, what physical property difference are you taking advantage of? Yeah. Say it. Starts with an S. O, L, U, B. Solubility. Table salt is soluble in water. Clearly sand isn't. Now when you poured the water into there, what's extracting what? The water is the solvent extracting one of the components of the mixture because it dissolves in the water. But now you got salt, water, and sand. You haven't really separated the salt from the sand yet physically, they're in the same container. One's in a solution, one's a solid. So what's step two?
Filtration.
Filtration.
Filtration. Now remember, you want to recover the salt in its original amount and form.
So you got six.
So,
You got the
Pour
salt.
water in using solvent extraction. Now you filter it. Now you've separated the solution that has the salt ions in it from the sand. But you're not done yet, because you don't have solid salt, you got
What if he doesn't?
a salt solution, so then what do you do?
Boil the salt water.
Well, you could if you cared about recovering the water. But remember, the water wasn't part of the original mixture. You added it. Remember, you added the water to separate the salt from the sand?
You boil it.
Could you do it evaporation?
Evaporation furnace, yeah, evaporate the water.
Yeah.
Now, if the water was there initially, if you had salt water and sand and you wanted to recover the water, you wanted the three components separated, fine, distill it. But the original mixture you had was just solid table salt and solid sand. So you don't care about the solvent. But the solvent served its purpose. It physically separated the sand from the salt, right? So what does solvent extraction take advantage of? Solubility. Now, there are cases where the solid, the components of the mixture maybe aren't solids mixed with solids. Solid mixed with solids, that's an easy way to do it. But sometimes you've got liquids that have impurities in it that are liquids. And you want to separate the two liquids from each other. So let's say the liquid you started with had two components in it, and you wanted to get one of them away from the other. Well, then you would add a second liquid that only one of the liquids mixed with. Now, when we're talking about liquid-liquid mixtures, normally we don't use the word soluble. We use the word miscible. M-I-S-C-I. So if two liquids mix with each other and form a liquid-liquid solution, we call those two liquids miscible. A great example of that is rubbing alcohol in water or ethanol in water. They're 100% miscible. You can mix them in any amount to form a solution. But it's not uncommon in organic chemistry where when we're preparing a particular, we're synthesizing a particular compound, that the chemical reactions in the synthesis end up having impurities in the liquid we wanted to make. And we have to get those liquid impurities out. And so we use solvent extraction, but it's liquid-liquid solvent extraction. So to the liquid-liquid mixture, the solution, we add a second liquid that only one of the liquids in that component dissolves it, or is miscible, and the other one isn't. Now, what does it look like when two liquids don't mix?
And water and like oil.
Water and oil. So what you see, I mean, if you got oil and vinegar dressing in your fridge, look at it before you shake it. You've got the oil on one layer, you got the water on the other. Good question is, if they're both liquids, why don't they mix? Why does water not mix with oil, ever? Why can't you get bacon grease out of the bottom of a frying pan by simply running it under hot water? It says water and oil never mix, and there's good reasons for it. But if I add a liquid that only one of those liquids is miscible with, but the other one isn't, then we're gonna see layers. And the more dense liquid would be on the bottom, and the less dense liquid would be on the top. But then the obvious question is, okay, cool, how do I separate them? Well, chemists use a little apparatus called a separatory funnel. Now this isn't actually the proper separatory funnel. It seems my separatory funnel in the lab has been broken. I found it actually in the summertime in the broken glass container. That little cardboard box, there's one in the science office.
That's crazy.
And my $300 separatory funnel is in there broken. I don't know who did it. I can't figure it out now. So I just made this really quickly. That's what a separatory funnel looks like, but it's supposed to have a valve on the bottom. Okay, so I just jury-rigged this from a burette. Okay, so it's not, this isn't the way they really look, but if this was part of this, it would be just fine. So let's say I have a liquid that has a mixture of two things in it, one of which I want to get out, okay? And let's say that this is the liquid. I only added blue food coloring for effect, so you can see the labels.
It literally just.
Now, you gotta make sure that that valve is horizontal, because if it's vertical, then it's gonna fall on the bottom, okay? So, let's say that that's got a liquid in it that I wanna get out, by adding to it a second liquid that only dissolves one of those liquids. So let's say this is my developing solvent, all right? So I pour that in, put this on, and then to make sure they mix, I invert them several times, and then what I do is, just gonna fit, yay, it will, and I let it sit, and then, let's see, what do I have handy here? Just donate those tin to the landfill. Now, the longer I let it sit, the better the separation the better the separation's gonna be. So, I don't know if you guys can see it, but you see the two layers? The idea was being, by inverting it several times, I mixed the impurities that were in here with my developing solvent. And the idea is, one of those things is in this layer, but the other one isn't. The one that's low solubility with this is still down there. And obviously, the original mixture is more dense than the solvent I added to it, so. And again, whatever is more dense will be in the bottom. Then all I do is drain off, and I usually let it sit for a good deal of time to make sure the separation is better. And then I just open this valve, drain off, I think I got some crud in here, drain off the more dense liquid. Yes, the valve from the burette I used obviously is effective. Once again, use my paperclip of science. This should work. And I gotta watch it so that when that interface gets right to the bottom, that I turn it off. Okay. And then the idea is the impurity that was in there is now in here. And I would do that because this is the thing I want to purify. I'm getting out something in there that I don't want in there by adding to it a liquid that dissolves only one of the components. So again, it's taking advantage of different solubilities. It's just not a solid solvent. Does that make sense? Now this is often, liquid solvent extraction is often not 100%, because you still have an interface where the two liquids met each other. So there's always a little bit of what was in here still in there. Okay? So maybe what this is now only maybe 85% of what was in there has been removed, then I would do it again. So if each solvent extraction is, say, 85% efficient, then the more times I do it, the purer the solution, or the purer the liquid that comes out of the bottom after each separation process, right? Now, I don't think we're going to use separatory funnels in Chem 11 or Chem 12, but at least one of the videos I'm going to show you in organic chemistry is a synthesis. It's called an esterification, and at the end of it, to purify the thing that we make called an ester, one of the things we have to do is use a separatory funnel. But that's, in a perfect world, if we have enough time later on in the year, we'll get to that, but I don't know if we even did last year, so. Anyway, that's the idea, that's the process, okay? And the big takeaway is, you don't have to draw a separatory funnel, but just realize that it's liquid solvent extraction. Whether it's solid liquid or liquid liquid, it takes advantage of the same property differences, namely solubility. Okay? What else do I want to go through here? Oh yeah, recrystallization. Gary mentions that one too, so I just kind of wanted to tell you what that is. Recrystallization is probably less of a, well, it's a separation technique, but it's mainly used for purification. So it's not uncommon that, you know, another separation technique would have been used prior to, okay? So let's say, how much time we got? Probably none, right? Does the class end at 9:30?
Yeah.
Okay, well, at least I'll tell you about it. Recrystallization, as the name suggests, involves crystallizing something. So let's say in this evaporating dish, I had a solid mixture of, let's say 99% sodium iodide and 1% calcium chloride. They both look the same. They both look like table salt. They're both soluble in water. You can't separate them by solvent extraction, and because they're both ionic compounds, obviously nothing associated with distillation or evaporation dryness would work. But what I want to do is get this away from this. In other words, I want 100% sodium iodide. So that solid mixture sitting in this evaporating dish. So what do? I add just enough water to dissolve all of them. So that in that evaporating dish, I got a really concentrated solution of calcium chloride, sodium iodide, right? I've added just enough water to dissolve. Notice the vast majority of ions in here are sodium ions and iodine ions, okay? Why? Because 99% of the solid is this. Only a tiny amount of the ions floating around in there are calcium and chloride. So now what I do is I carefully heat it. I'm not going to evaporate this to dryness, but I'm going to carefully heat it. And as I heat it, and the water vaporizes, which of these two solids is going to crystallize first? The one that I've got hardly any of, or the one that I've got 99%? Take a guess. This one. This solution is full of sodium and iodine ions. It's not nearly saturated with respect to calcium chloride because there's hardly any of them there. This is what I have the vast majority of. So as I cool it, or as I evaporate the liquid, the first solid that I see
Staff and students,
has to be
come get your Como grants and March to Mercer tickets in the cafeteria today at